To calculate voltage drop, you can use the formula voltage drop equals 1.732 times K times I times D divided by Cm, where K is the constant for the conductor, I is the current in amps, D is the distance one way in feet, and Cm is the circular mils of the conductor. Given a 1600 amp breaker at 480 volts, 60 Hz, and a distance of 1000 feet, and using a K value of 12.9 ohms, you'll need to determine the appropriate circular mils value to complete the calculation. The example suggests finding circular mils using the formula circular mils equals D divided by Coulomb times K2, where D is the distance one way in feet, Coulomb is 10 for copper conductors, and K2 is 5280 for converting feet to miles. Using the given distance of 1000 feet, the calculation yields circular mils equals 1000 feet divided by 10 times 5280, which equals 0.1893 miles. Plugging these values into the voltage drop formula, you get voltage drop equals 1.732 times 12.9 ohms times 1600 amps times 1000 feet divided by 0.1893 miles, which equals 48.84 volts. The National Electrical Code, or NEC, recommends limiting voltage drop to 5% of the nominal voltage. For a 480 volt system, this means keeping the voltage drop below 24 volts. In a calculated example, the voltage drop is 48.84 volts, which exceeds the recommended limit. To avoid excessive voltage drop, consider firstly using larger wire. A larger wire will have a lower resistance, which reduces voltage drop. Secondly, shorten the distance if possible. Reducing the distance between the source and the load will inherently decrease voltage drop. Thirdly, install voltage regulators. Voltage regulators can compensate for voltage drop by adjusting the voltage to maintain a stable level. Fourthly, consider parallel wiring. Running multiple wires in parallel can increase the current carrying capacity and reduce voltage drop. Finally, use power factor correction. Improving the power factor can reduce the current draw, thus reducing voltage drop. When calculating voltage drop, remember that the formula voltage drop equals 1.732 times K times I times D divided by Cm is applicable for three-phase systems. For single-phase systems, a slightly different formula may be used. Typically, voltage drop equals 2 times K times I times D divided by Cm. Ensure you are using the correct formula based on the system type. Selecting the appropriate wire size is critical. The circular mils, or Cm, value determines the wire's cross-sectional area and its ability to carry current without excessive voltage drop. Consult NEC tables to determine the appropriate wire size based on the current, distance, and allowable voltage drop. NEC table 310.15 is a good starting point. Remember that ambient temperature and the number of conductors in a raceway can affect the ampacity of the wire, so apply appropriate correction factors as specified in the NEC. Voltage regulators are effective at maintaining a stable voltage level at the load, especially when voltage fluctuations are common. There are various types of voltage regulators, including automatic tap changing transformers and solid-state regulators. Choose the appropriate type based on the specific application and voltage requirements. Parallel wiring involves running multiple conductors per phase and neutral to increase the overall current carrying capacity. When using parallel conductors, ensure that they are the same length, material, and have the same termination methods to ensure equal current sharing. The NEC has specific requirements for parallel conductors, including minimum size and proper termination. Power factor correction involves adding capacitors to the electrical system to offset the inductive reactance of motors and other inductive loads. Improving the power factor reduces the overall current draw from the source, which in turn reduces voltage drop in the conductors. Power factor correction can also improve energy efficiency and reduce utility bills. When dealing with large loads and long distances, it's often necessary to use a combination of these methods to effectively manage voltage drop. For instance, using a larger wire size in conjunction with power factor correction and a voltage regulator may be the optimal solution. Always consult with a qualified electrical engineer to determine the most appropriate and cost-effective approach for your specific application. Consider the impact of harmonic currents on voltage drop. Harmonic currents can increase the effective current flowing through the conductors, leading to increased voltage drop. If harmonic currents are present, you may need to use larger conductors or harmonic filters to mitigate their effects. Always follow the NEC guidelines for conductor ampacity and voltage drop calculations. The NEC provides specific requirements and recommendations to ensure the safe and reliable operation of electrical systems. Failure to comply with the NEC can result in equipment damage, fire hazards, and electrical shock. In addition to the calculated voltage drop, consider the voltage drop in the source impedance. The source impedance, such as the utility transformer or generator, can contribute to the overall voltage drop in the system. Consult with the utility company or generator manufacturer to determine the source impedance and factor it into your voltage drop calculations. Regularly inspect and maintain electrical systems to identify and address potential voltage drop issues. Loose connections, corroded conductors, and overloaded circuits can all contribute to voltage drop. Periodic inspections and maintenance can help prevent these problems and ensure the reliable operation of the electrical system. When selecting conductors, consider the conductor material. Copper conductors have a lower resistance than aluminum conductors, which can result in low voltage drop. However, copper conductors are also more expensive. Choose the appropriate conductor material based on the specific application requirements and cost considerations. When installing conductors, ensure that they are properly supported and protected from physical damage. Damaged conductors can have increased resistance and contribute to voltage drop. Follow the NEC guidelines for conductor installation and support. Consider using voltage drop calculation software to simplify the process and ensure accuracy. There are many commercially available software packages that can perform voltage drop calculations based on various parameters, such as conductor size, distance, current, and power factor. These software packages can also help you evaluate different design options and optimize the electrical system for minimal voltage drop. Ensure that all electrical equipment is properly grounded. Grounding provides a low impedance path for fault currents, which can help reduce voltage drop during fault conditions. Follow the NEC guidelines for grounding electrical equipment. Consider the impact of motor starting on voltage drop. Motor starting can cause a significant voltage dip, which can affect the performance of other equipment connected to the same electrical system. Use motor starters with reduced voltage starting methods, such as auto transformers or part winding starters, to minimize the voltage dip during motor starting. When designing electrical systems for sensitive electronic equipment, such as computers and programmable logic controllers, consider using dedicated circuits with voltage regulation to ensure a stable voltage supply. Sensitive electronic equipment can be susceptible to voltage fluctuations, which can cause malfunctions or data loss. Follow manufacturers' recommendations for voltage requirements and grounding. When calculating voltage drop for nonlinear loads such as electronic ballasts and variable frequency drives, consider the impact of harmonic currents on the voltage drop. Harmonic currents can increase the effective current flowing through the conductors, leading to increased voltage drop. Use harmonic filters or oversized conductors to mitigate the effects of harmonic currents. Regularly monitor the voltage levels at various points in the electrical system to identify potential voltage drop issues. Use a voltmeter or power quality analyzer to measure the voltage levels under different load conditions. Compare the measured voltage levels to the nominal voltage levels and investigate any significant deviations. When designing electrical systems for emergency power systems, such as generators and uninterruptible power supplies, consider the impact of voltage drop on the performance of the emergency equipment. Emergency equipment may have specific voltage requirements and tolerances. Ensure that the voltage drop is within the acceptable limits to ensure reliable operation of the emergency equipment. When using step-down transformers, consider the impact of transformer impedance on voltage drop. Transformer impedance can contribute to the overall voltage drop in the system. Select transformers with low impedance to minimize the voltage drop. When designing electrical systems for renewable energy systems, such as solar photovoltaic systems, consider the impact of voltage drop on the performance of the renewable energy equipment. Renewable energy equipment may have specific voltage requirements and tolerances. Ensure that the voltage drop is within the acceptable limits to ensure reliable operation of the renewable energy equipment. Consider the use of active voltage conditioners to mitigate voltage drop issues. Active voltage conditioners use electronic components to actively regulate the voltage and compensate for voltage drop. They can provide a stable voltage supply to sensitive equipment and improve the overall power quality of the electrical system. Regularly calibrate and maintain all voltage measuring instruments to ensure accuracy. Inaccurate voltage measurements can lead to incorrect voltage drop calculations and potentially unsafe operating conditions. Follow manufacturers' recommendations for calibration and maintenance. Remember to always prioritize safety when working with electrical systems. To energize the circuit before performing any work and follow proper lockout-tagout procedures to prevent accidental energization. Wear appropriate personal protective equipment, such as safety glasses and insulated gloves. Consult with a qualified electrician if you are not familiar with electrical work. Consider using energy-efficient lighting and equipment to reduce the overall current draw and minimize voltage drop. Energy-efficient lighting and equipment consume less power, which can help reduce the voltage drop in the conductors. Regularly review and update electrical system designs to account for changes in load and equipment. Changes in load and equipment can affect the voltage drop in the system. Review and update the electrical system designs to ensure that the voltage drop remains within acceptable limits. Consider using demand-side management techniques to reduce the peak demand on the electrical system. Demand-side management techniques can help reduce the overall current draw and minimize voltage drop. Consider using smart grid technologies to improve the monitoring and control of voltage levels in the electrical system. Smart grid technologies can provide real-time voltage monitoring and control, which can help prevent voltage drop issues. Consider the use of distributed generation to reduce the distance that power needs to be transmitted, thereby reducing voltage drop. Distributed generation involves generating power closer to the load, which can reduce the distance that power needs to be transmitted and reduce voltage drop. Remember to consider all relevant factors when calculating voltage drop and implementing voltage drop mitigation measures. Factors such as conductor size, distance, current, power factor, harmonic currents, source impedance, transformer impedance, and equipment voltage requirements can all affect the voltage drop in the system. By considering all of these factors, you can design and maintain electrical systems that provide a safe and reliable power supply with minimal voltage drop. Remember that the NEC is a minimum standard and that you may need to go above and beyond the NEC requirements to ensure the reliable operation of your electrical system. Voltage drop calculation is an iterative process that may require adjustments to the design to achieve the desired results. Continuous monitoring and analysis of the electrical system can help identify and address potential voltage drop issues before they become problems. Finally, documentation of all voltage drop calculations and mitigation measures is essential for future reference and troubleshooting. Accurate documentation can help ensure that the electrical system is properly maintained and that any future changes are made in a way that does not compromise the voltage drop performance.